So we're talking about the conditions for creating a confidence interval for population proportions. The conditions are the same when we had a sampling distribution for proportions. So the first condition is that it has to be random. So either it has to come from an SRS if you're sampling, or there has to be random assignment if you're conducting an experiment. We also have to make sure that we have independence, so that it's independent. So random sampling helps ensure independence, which allows us to use the standard deviation formula, and we check the 10% condition for independence, which states that our sample size n has to be less than or equal to 10% of our population, capital N. And the last thing we have to check is normal. Okay. And when we're making sure that we have a normal distribution, we use the large counts condition, which, because we're looking at p hat, that means n times p hat has to be greater than or equal to 10, and n times 1 minus p hat has to be greater than or equal to 10. So when we were dealing with sampling distributions for sample proportions, all right, we did not know P from our populations, so we are replacing P with P hat. And when we do so, instead of calculating a standard deviation, we calculate something called standard error for the sample proportion P hat. So this will help us describe how close the sample proportion P hat will typically be to the population proportion in repeated SRSs of size n. So that gives us is now our standard deviation formula for P hat is based off of P hat instead of P. So we're going to have the square root of P hat times 1 minus P hat all over n. So we have our standard error, which is when the standard deviation is estimated from sample data. And then we're going to have our critical value, which is the z-score that sets the boundary for our confidence interval. So how many standard deviations on either side do we want to go, which is called z-star or z-statistic. So we are going to be calculating our z critical value based on our level of confidence. And the way that we're going to get our z critical value is by using INV norm on the calculator. So when we're calculating our z critical value, we're going to look at 4 pretty common confidences that we're typically going to see. By no means are these inclusive. We could look at other ones. And no matter the confidence, you can calculate your z critical value. So just to kind of refresh how this works, if I'm looking at 80% confidence, there are 2 z critical values, a positive and a negative, where we can be certain that the middle 80% of our data is contained. So this middle part here is our middle 80%, which leaves us with 20% split evenly above and below. So 10% above and 10% below. So our z critical values are for that 10% below and above. So if we want to get one of them, we use INV norm. And typically we're going to use the area below. So our area is going to be 0.10, mean of 0, standard deviation of 1. Now that is going to give us a negative z critical value, but for our purposes, we're going to identify it as positive for now. And then when we get to our confidence interval formula, we'll see how the negative comes back into play. So we're going to get 1.28. Okay, I'm not going to draw the picture for the rest of these. I'm just going to go over how we find that Z critical value using I and V norm. Okay, so for 90% confidence, we have 10% that is split evenly, which means our area is 0.05. Our mean and standard deviation are 0 and 1 for all of these, so I'm not really going to go over those, but area is 0.05. So that's going to give us a Z critical value of 1.65. 95% confidence, we're going to have I and V norm. So we have an area of 5% that gets split evenly, which is 2.5%, which is 0.025. Which gives us a Z critical value of 1.96. So we can see the more confident we want to be, the larger the Z critical value, because it's more standard deviations to include more of the data. And the last one, 99% confidence. That's 1% split in half, which is half of a percent, which is 0.005. Which is going to give us a Z critical value of 2.58. You are not required to memorize any of these Z critical values, but these ones are going to pop up quite often. So just be on the lookout. Okay. So now that we've discussed all of these things, let's talk about the actual formula. So it starts with our point estimate, which we've now discussed is P hat, plus or minus our critical value, which we've now defined as Z critical value, times our standard deviation, which we have said is the square root of P hat times 1 minus P hat all over N. So Z star is our critical value, and with C% of its area between negative Z and positive Z. And this is called a one sample Z interval for proportions. So what we're going to be doing when we are finding a confidence interval is following the very similar four-step process that we did for sampling distributions. So first thing we have to figure out is what our parameter is in words. Like, what are you trying to estimate? Then we're going to use our C confidence to figure out what our critical value is. Okay. We're going to then check our three conditions, random, independent, and normal. As long as the conditions are met, we're then going to use our formula and plug in our P hat, Z critical value, and N. After you show the values that are substituted in, you can either construct the rest of the interval by hand, or you can use the calculator. So if you go to calc and then over to tests, the very first thing A should say 1 prop Z int, and that means one sample Z interval for proportions. And then you're going to write what the interval is, and then the last step is to interpret the interval in the context of the problem. So let's do an example. The Gallup Youth Survey asked a random sample of 439 U.S. teens aged 13 to 17 whether they thought young people should wait to have sex until marriage. Of the sample, 246 said yes, Construct and interpret a 95% confidence interval for the proportion of all teens who would say yes if asked this question. So our parameter that we're trying to look at, so P, is the teens who would say yes. Okay. We're looking at a 95% confidence, which gives us a Z critical value of 1.96. Okay. I'm also going to go ahead and calculate my P hat, which more often now you're going to have your sample size with the number who responded yes or positive. So that's going to be 246 over 439, which is going to be 0.56. And then we have our N, which is 439. Okay. Now I'm going to check my condition. So the first one I'm going to check is random. And it does say we took a random sample. Next, I'm going to check independent. So my sample of 439 has to be less than or equal to 10% of all teens, which there's at least 4,000 of those, so we're good there. And the last one is normal. So 439 times 0.56 has to be greater than or equal to 10, and 439 times 0.44 has to be greater than or equal to 10. And both of those are true. So now that we have all of our conditions, we can go ahead and construct our interval. So it's going to start with our P hat, which is 0.56, plus or minus our Z critical value, 1.96, times the square root of 0.56 times 0.44 all over N, which is 439. So at this point, you can finish constructing your interval using your calculator, or you can go ahead and do the math and construct it that way. Both are acceptable. So if I'm going to use my calculator, I'm going to do the square root, I'm going to do 1.96, times the square root of 0.56 times 0.44 over 439. And I'm going to get 0.56 plus or minus 0.0464. So that's going to give me an interval of 0.5136 to 0.6064. You're going to use the calculator, you're going to go to stat, you're going to go to tests, and then you're going to go all the way down to A, which is where one prop Z int is. So it's going to ask you for your X value, and the X is your number who say yes, which in this case is 246. You're not actually going to plug in a proportion. You're going to plug in a number. N is your sample size, which is 439. And my C level is going to be your confidence as a decimal. And it's going to automatically put 0.95, and that's what it is. Then we're going to hit calculate. And it's going to give us our interval typically to 6 decimal places, but I only really care about 4. And to 4 decimal places, it's 0.5139, and then 0.6068. So to 3 decimal places, it is the same. To 4 decimal places, it's slightly different. But like I said, I will accept both as correct answers. So my last step is to now write my sentence. So it's going to start with, we are 95% confident that the true proportion of teens who would say yes is between 0.514 and 0.606. And those are all of my steps. So let's look at one more example. So this time I have a random sample of 250 high school students. It was found 85% of them later graduated. And we want to find the 98% confidence interval for the true proportion of all high school students who graduate. So P is the proportion of high school students who graduate. We're looking at 98% confidence, which gives me a Z critical value of 2.33. This time I am specifically given P hat. I'm not giving an X and an N. I know P hat is 0.85, which actually does make it more difficult to use the calculator because I have to basically back solve for what X is. And X isn't guaranteed to be a whole number this way, and I want X to be a whole number. And then lastly, we are given N, which is 250. So now we can go ahead and check our conditions. So for random, it does say we are taking a random sample. Independent, 250 has to be less than or equal to 10% of all high school students. And there's at least 2,500 of those, so we're good there. And then lastly, normal, 250 times 0.85 has to be greater than or equal to 10, and 250 times 0.15 has to be greater than or equal to 10, which it is. Okay. So for my confidence interval, we're going to have 0.85 plus or minus 2.33 times the square root of 0.85 times 0.15 all over 250. So in the calculator, I have 2.33 times the square root of 0.85 times 0.15 over 250. So I'm going to get 0.85 plus or minus 0.0526, which is 0.7974 to 0.9026. If I wanted to use my calculator here, I would first have to figure out what 85% of 250 is. So I have to do 0.85 times 250, which is 212.5. And I'm not allowed to plug in a decimal for X for the calculator when I go to tests. So that means I either have to use 212 or I have to use 213 for my X. I can't use the exact value. So if I use 212 and my sample size is 250, my sea level, I'm going to change to 0.98. I calculate it. I'm actually going to get 0.7952 to 0.9008. So smaller. And if I use 213, I get 0.7998 and 0.9042. So a little bit higher. So I would, in this case, where you're given a specific percentage and not an X value, I would not use the calculator. So my last step is to write the sentence. So we are 98% confident that the true proportion of high school students that graduate is between 0.797 and 0.903. The last thing we have to discuss is sample size and margin of error. So in the field where confidence intervals and significance tests are run, researchers need to limit both the margin of error to a fixed amount, but still maintain a certain confidence level. So the only thing that you can then vary and thus control is your sample size, because the value for p-hat is something that's out of control. Like, you don't know what your sample proportion is going to be, so you can't control it. So to determine the sample size you need, we first look at this piece of the confidence interval formula that accounts for margin of error. So the margin of error is the z critical value times the square root of p-hat times 1 minus p-hat all over n. And if I were to solve that formula for n, and I'm not going to go through the process, I would get n equals your z critical value over the margin of error squared times p-hat times 1 minus p-hat. So that's the formula we'll use to solve for the necessary sample size. Now, we will obviously know our margin of error that we want to attain. We'll know the level of confidence, which will give us our z critical value. But we don't know p-hat. Like, we won't know what our p-hat is until we can conduct the study. So how am I able to solve for n? So we do one of two things. We either use an estimated p-hat based on a previous study, and this would be wording used in the problem. They would say, in a previous study, the proportion was found to be, and then they'd state it. Or we use the conservative p-hat of 0.5. And using a p-hat of 0.5 gives the largest possible margin of error for any given z or n. And this second one is the most common method we're going to be using. We will use that one most often. So we look at an example. It says, before conducting nationwide polling prior to a national election, most good companies will decide ahead of time how many people to include in the poll based on a particular margin of error and confidence interval. Let's say that Gallup wants to conduct a poll to see what proportion of the voters would vote for Donald Trump again if Donald Trump were running for president against Elizabeth Warren. Gallup wants to be 95% confident with a margin of error of no more than 3 percentage points. How many people must they randomly sample in order to achieve this? So our margin of error is going to be 0.03. Our z critical value is based off the 95% confidence, which gives us 1.96. They did not mention a previous sample proportion, so we're going to use a p-hat of not 0.05, 0.5. So now I'm just plugging those into my formula. So I'm going to have n equals 1.96 over 0.03 squared times 0.5 times 1 minus 0.5, which is still 0.5. And then I just plug it into a calculator. And I can plug it into a calculator just like that. And we're going to get n is 1067.11 repeating. And because we can't have a decimal for sample size, we're always going to round up, which in this case is going to be 1068. Let me know if you have any questions about constructing confidence intervals, interpreting confidence intervals, or solving for sample size.